In this section, we'll be talking about a technique of identifying points on a coordinate plane, not so much according to horizontal and vertical distances as we've been accustomed to, but in terms of an angle and a distance along the terminal side of that angle. Here's what I'm talking about. Suppose we have a point 3, 4 on the coordinate plane, and suppose we think about generating an angle from standard position to that point, that is, an angle that we might call theta, like this. And then along this ray, we define a distance to that point. You see, it's just another way to describe the same position in the coordinate plane. Now we're going to call the distance here r, and the angle will be theta. And we can understand very quickly how this angle and this angle and distance r can be calculated. The coordinates here are 3, 4, so that's 3 and 4 here on our little right triangle. And let's see, the r value would be calculated according to the Pythagorean relationship. R squared is equal to 3 squared plus 4 squared, or r is the square root of 3 squared plus 4 squared. Let's put that down over here. R squared is x squared plus y squared. R then is the square root of the sum of those squares. And for this particular problem, r is 3 squared plus 4 squared under the radical. Well, that's 9 and 16, that's 25. So the distance r is 5 for this problem. And it's important for us to know the general idea for the calculation of r, though. Now for theta, it's a similar kind of thing. We can just use past experience to understand how to find the theta. And we have information about opposite side and adjacent side, and that's the tangent ratio. So the tangent of theta is 4 over 3, and more generally it's y over x in this kind of configuration. So tangent theta is y over x, and this is how we make the calculation for theta. In our problem, it's 4 over 3. Inverse tangent then of 4/3 would give us a theta of approximately 53 degrees. Now, this same point then can be described in terms of an ordered pair, but not horizontal and vertical distance. It's the ordered pair of a distance of 5 and a theta of 53 degrees. A lot of times in using this polar form, this is called polar form or maybe trigonometric form, in using this polar form, it's handy to use a polar coordinate plane like this. Notice it's not so much an XY plane, but it's a plane on which we can see angles very easily and measure distances along those angles. And it really doesn't make any difference if you have polar coordinate graph paper, but if you have access to that, you might pick some up because it's really neat to find points on this polar coordinate plane. Let's do that with a few points here. If we're talking about 3 and pi over 4, then we would first look at an angle of pi over 4. And we know that to be a 45-degree angle. And that would be this angle. You see, we would have this ray. And then along that ray, we're going to go a distance of 3. Well, let's see. Now I have I've made marks here along the horizontal axis, and I'm just going to kind of follow those up on our ray. So it's a distance of 1, 2, 3. So here's the 1, 2, 3. So here then is the point 3 pi over 4. Now, if you don't have polar coordinate paper, it's real easy to produce these same angles, you know, on a coordinate plane, a rectangular plane. And if we're thinking about an angle of pi over 4, we're looking at it like this, you see, and then we just measure 1, 2, 3 along that ray. And there we are at the same position. So, very, very much equivalent situations, but here we can measure the angles, and we can see the angles a bit more accurately. And by the way, as you look at this, is there any wonder that it's called a polar coordinate system? It kind of looks like we're looking down on the North Pole or the South Pole, you see, and we have our lines of longitude and latitude here drawn into our polar coordinate plane. Well, at any rate, let's identify the positions of other points. Before I get off of the polar coordinate plane, these little kind of outward radial kinds of things, this is 15 degrees if you have this kind of paper. So it's 15, 30, 45, 60, 75, and then 90 degrees. So we have some nice little splits here on the polar coordinate plane to give us great accuracy in the graphing process. All right, at any rate, -2, 30 degrees. Well, let's see. If we go 30 degrees, that's this angle. But we want to go -2 along that angle. -2, that's the negative direction. So that means we have to extend that 30-degree angle back this way. We have to take that ray, and as we turn it 30 degrees here, we have to think about it extending in both directions, because a distance of -2 means -2, that's out this way. You see, that would be right here. Now, this pretty much tells us that the coordinates of points located on a polar coordinate plane using polar coordinates is not unique. There are a lot of ways of describing this position. One way is this 30-degree angle with a distance of -2. Another way would be to describe an angle of, well, let's see, 180 plus 30. 180 plus 30, that's 210. You see an angle of 210 degrees and then a positive distance of 2. You see, so, and then we could describe the angle as one of any angle which is coterminal with this one. So there are really an infinite number of ways of describing positions. How about 5, -60? So we have a negative angle generated from this standard position. And let's see, -60 degrees, I've got 30 here, I've got 60 about right here. So here's a -60-degree angle. See, there's a -60-degree angle. And now 5 along that angle, let's see, 1, 2, 3, 4, 5. So here's that point. So here's 5, -60 degrees. How about -3, -3 pi over 4? You know, one thing I find intriguing about polar coordinates is that you locate positions not so much in the order in which the numbers are given. Here we're given a distance and then the angle, but really we need the angle before we measure the distance. You see, it's kind of a funny juxtaposition of thinking here when we locate points this way. Okay, let's see, -3 pi over 4. Let's see, we're measuring the angle in the negative direction. 3 pi over 4, that would be an angle that goes around to right here. Now the angle is measured this way as a negative angle. It could have been measured this way. The coterminal angle measured this way would be the same thing. But at any rate, here's that angle. But then we want -3 from here. So here's our sort of terminal side of that angle, but we want -3. So we need to go out in that direction, you see. So we're going to think about going in this direction, a distance of 3. So 1, 2, 3. Oh, here's this same spot that we had located before as 3 pi over 4. So a lot of ways to accomplish getting to the same position on this polar coordinate plane. Now, let's talk about changing from rectangular coordinates to polar coordinates, and also polar coordinates to rectangular coordinates. All right, we know from what we just talked about, if we have rectangular coordinates of x, y, then we can calculate polar coordinates by making the calculation for r as the square root of x squared plus y squared, and the calculation for theta as tangent theta is y over x. So it's the inverse tangent of y over x to find theta. And now we have the polar coordinates of that point as an r comma theta value. Now what about taking an r theta, you see, and going back into rectangular coordinate form? Well, it's really easy to understand how that takes place. If we have an angle theta and a distance r, let's say to this point, then we know there's an xy associated with that point. And if we think about our trig ratios just for a moment, we understand a relationship between x, theta, and r. You see, and that's all we want to do is involve x with the theta and r, y with the theta and r, and we have a way of making the calculations For x, you know, x is from the perspective of this angle, it's the adjacent side, and r is the hypotenuse. So that's just the cosine notion. So the cosine then of theta is x over r, and multiplying on both sides by r, we find that x is r cosine theta. And in a similar way, sine theta is y over r. So multiplying on both sides by r, we find y is r sine theta. So here's our x and here's our y, and our ordered pair then, in our xy configuration, in our rectangular form, would be, well, let's see, it would be r cosine theta, r sine theta. So r cosine theta, r sine theta, for the coordinates of the point r theta. All right. Now let's go through the process of changing 830 degrees into a more rectangular form, the rectangular coordinates associated with these polar coordinates. Well, x is r cosine theta, so x then is, and just take the information right from the coordinates here, so it's 8 cosine 30 degrees, but cosine 30 degrees is the square root of 3 over 2. The 2 and the 8 cancel, leaving 4. 4 root 3 then is the x component. And then for y, it's r sine theta, so it's 8 times sine 30 degrees. Sine 30 degrees is 1/2, half of 8 is 4, so the y component is 4. And the rectangular coordinates then would be 4 root 3 and 4, corresponding with 8 and 30 degrees. Let's write the polar coordinates corresponding with these rectangular coordinates. We begin by identifying r as the square root of x squared plus y squared. X is -3, y is 5, so we find r to be the square root of 34. Theta is found by calculating tangent theta is y over x. Y over x is 5 over -3, so we take the inverse tangent of -5/3 to find theta to be approximately -59 degrees. Now, in this process, notice that we're taking inverse tangent, and because of that, we are sort of confined to a couple of quadrants, because inverse tangent is going to either put us into the first or fourth quadrant. But a lot of times, the angle that we want lies in the second or third quadrant. We have to be careful about that. Now, in this problem, that's the dilemma that occurs. The -3, 5 is a point in the second quadrant, so what we're really looking for is an angle theta like this. But what we calculated is an angle theta down here. We calculated this to be -59 degrees. So what we have to do to accommodate the situation is just take this -59 degrees and add 180 degrees, you see, to point us in the right direction. So -59 degrees plus 180 is 121 degrees, and in the r theta form, our point is the square root of 34 and 121 degrees. So we have to be careful when we go from rectangular form to polar form. Now let's extend our idea about this conversion from rectangular to polar, polar to rectangular. Let's extend it to the notion of equations. You know, an equation in x and y has solutions that we can think of as rectangular form solutions in rectangular form, xy pairs. Now suppose we take those xy pairs, those solution points, and replace them with polar coordinates, and then put them right back into the equation. Then we can imagine the idea of going from a rectangular equation into a polar equation, and a polar equation into a rectangular equation. Let's go through that process. Now, to go from a rectangular equation into a polar equation, it's really almost a trivial idea, because x can be replaced with r cosine theta and y replaced with r sine theta, and then we just kind of manipulate from here if we'd like to do that. But this is the polar equation corresponding with this rectangular equation. Now, a lot of times in the polar world, just like in the rectangular world, we sometimes write equations in a function format. Now with rectangular equations, that function idea is to solve for y. So we write y equals some expression involving x. And in the polar world, a lot of times we write r as a function of theta. That is, we isolate r on one side of the equation, and on the other side we have an expression involving theta. Now, if we wanted to manipulate to that form here, we could do it rather easily by identifying this common factor of r in these two terms, pull r out as a common factor, and we have 3 cosine theta minus sine theta. And I've subtracted 2 on both sides to accomplish the negative 2 on the right side. Dividing on both sides by the binomial, I find r to be this fraction. Okay, so going from rectangular equations to polar equations, no big deal. Going the other way, though, is quite challenging, or it can be quite challenging because of the limited substitutions that we make. We have some interesting opportunities for substitution, but look at what they are. We have to be looking in our polar equation at an r squared in order to replace with x squared plus y squared. We have to be looking at a tangent theta to replace with y over x. You see, all we're trying to do is trade in the notion of r and theta with the notion of x and y. But gee, we have to have some very special kinds of factors and terms involved for that replacement to take place. And we also could replace an r cosine theta with x and an r sine theta with y. So we're looking for these kinds of items in our polar equation in order to make the substitution. All right, to become accustomed to the idea and the manipulation possibilities, let's just take a couple of degenerate equations in polar form. Now the rectangular counterpart would be to take degenerate equations that would be something like y equals 3. Well, we know what that is. That's a horizontal line going through a certain spot on our coordinate plane. And x equals negative 5. We know what that would be, a vertical line. We know where it would go on our coordinate plane. But what about this in polar form? How about just something like, oh, r equals 5? Now this is a distance of 5 and no angle is given. So it's a distance of 5 for every angle. For every angle. A distance of 5 for every angle from the origin means every point that's a distance of 5. Oh, that's just a circle. You see, it's a circle whose radius is 5. Well, how do we accomplish this idea algebraically? Well, we do this. I'll square on both sides, and we have r squared is 25. Now, r squared we can replace with x squared plus y squared. And we do indeed see that we have the equation of a circle whose radius is 5 and whose center is at the origin. Here's another degenerate polar equation. Theta is 76 degrees. What does this mean? Well, it means for an angle of 76 degrees, any distance, every distance is associated with that. So it's the notion that if we identify that angle, you see, every distance associated with that angle means that we want all of these points. You see, we want the equation corresponding with that line. How do we arrive at that? Well, here we understand that our substitutions have to do with tangent theta, cosine theta, sine theta. So we want to apply one of those trig ratios to both sides of this equation. And here's what we do. Just apply tangent theta on both sides. We'd have this. Now, tangent 76 degrees is about 4, so this is tangent theta is equal to 4. Now, tangent theta can be replaced with y over x. So this is y over x then equals 4. And here's our rectangular form, you see, of the equation. And if I multiply on both sides by x, I find this to be y equals 4x. Here's another one. R is 2 cosecant theta. Your first thought could be to rewrite using our reciprocal identities in terms of sine, cosine, and tangent. And here that strategy works really well. Cosecant theta is 1 over sine theta, and now our fraction here becomes 2 over sine theta. Multiplied by sine theta on both sides, we have r sine theta is equal to 2. And now we have a substitution For r sine theta, it's simply y. So this is y equals 2. In manipulating polar equations for rectangular form, the situation can become algebra intensive very, very quickly. But it's important to kind of stay focused on what we're trying to accomplish. We have only certain forms that we can replace with x's and y's. We have a replacement. If we see an r squared, we have a replacement. If we see tangent theta, we have a replacement. If we see r sine theta or r cosine theta, we have a replacement. But we begin problems kind of like this. I mean, we might see sine 3 theta over here. What are we going to do with that? Well, we have some manipulation opportunities here. We can think of 3 theta as 2 theta plus theta. And now we have an identity involving the sine of the sum of angles. And applying that identity, it's the sine of the first angle times the cosine of the second one plus the cosine of the first angle times the sine of the second angle. Now, what are we going to do with these rascals? Well, we have a sine 2 theta here. Double angle. Oh, we have an identity for that. Sine 2 theta is 2 sine theta cosine theta. And this cosine theta I'm bringing down as a separate factor. And then we march over here and let's see. Cosine 2 theta. We recall that there are actually 3 replacements that are possible for cosine 2 theta. I'm choosing the one that is cosine squared theta minus sine squared theta. Now this sine theta remains as a factor over here and has to be multiplied into this binomial in the second step. While we're over here, let's have a look at that next step. It's sine theta times cosine squared theta. So we have, let's see, where is this rascal? Oh, it's sine theta times cosine squared. That's this multiplication, and then sine theta times sine squared theta is sine cubed theta. Wow, this is getting more complicated by the minute. Let's go back over here. This business, cosine theta times cosine theta becomes cosine squared theta. And then here are our other factors. Wow, what are we going to do next? Well, let's see. Now look at the structure of the 3 terms that are here. I have 2 terms that are like terms. Now notice they're like terms because they both involve sine theta times cosine squared. Sine times cosine squared, you see. So we have 2 of these things plus another one. That's 3 of those things. You see, it's 3 sine theta cosine squared theta, and then bring down the minus sine cubed theta. Whew, okay, we've consolidated a little bit here. Now I see 2 times these 2 terms, so let's go ahead and expand that out. 2 times 3 of these things, you see, gives 6, and then 2 out here as a factor becomes minus 2 sine cubed theta. Now, let's understand at this point what we're trying to accomplish. When we have sine squared theta or cosine cubed theta, that means that we just have 2 or 3 factors of sine or cosine. Now, if we can somehow attach an r factor with each of those factors of sine and cosine and so forth, then we have a replacement opportunity. So let's kind of string things out here. We've got 6 sine cosine squared, but cosine squared means cosine times cosine. And I'm just writing this for emphasis because I want us to see a certain pattern that emerges here. Sine cubed theta means we have 3 factors of sine theta. Now if I can somehow attach an r factor to each of these, then I've got some nice replacements. So let's think about that. If I attach an r factor here, I would have an r factor here, an r factor here, an r factor here. That's r cubed then. 3 factors of r have to be introduced into this particular term. And over here, I also need 3 factors of r in order to create r sine theta, r sine theta, r sine theta. So I need to introduce 3 factors of r in that term as well. Well, if I'm going to introduce r cubed in both of these terms on the right side of the equation, then I have to introduce r cubed over here as well. So I'm thinking about multiplying r cubed times r and r cubed times both of these terms. And here is what emerges. Now r cubed times the r on the left side just gives us r to the 4th power. When I multiply r cubed times the 2 terms on the right side, I'm going to kind of distribute them out. You see, I'm not going to write r cubed. I'm going to say, okay, I want one of those r factors to go with that sine theta factor, and another r to go with cosine theta, and that third r to go with cosine theta. And now in my last term, I'm walking over here we go. The last term, I have 3 factors of r that I'm now distributing through the various, the 3 sine theta factors. So r sine theta, r sine theta, r sine theta. Now r sine theta is simply y, so this is going to be replaced with a y factor, a y factor, a y factor. See, that's the idea. So we're going to have minus 2y cubed right here. But let's make the replacement, and just for emphasis now, I'm just making the replacement of letters in here. So r sine theta, y, r cosine theta, x, r cosine theta, another x, and then the minus 2 and the 3 factors of y from over there just a moment ago. All right, now on the left, notice I have r to the 4th power. I don't have a replacement for r to the 4th power, but I do have a replacement for r squared. So I can think about r to the 4th as being r squared squared. Therefore, I can take the r squared part and replace with x squared plus y squared. So I have x squared plus y squared squared. And on the right, I just consolidate matters with multiple factors and using exponents. I've got, let's see, x times x is x squared times the y. So I have 6x squared y for this term and 3 factors of y here. So here then is our equation in rectangular form that corresponds with the original equation in polar form.